So we had talked about when we want to solve a quadratic, we set it equal to 0. When we want to solve a square root, we get the square root by itself. Does anybody remember what we needed to do to solve an absolute value? You want to get it by itself? So let's look at it this way. If absolute value of x equals 7, what values can x be? 7 or negative 7. Okay? If x plus 1 equals 7, then x could be 6 or negative 8. And the way we would come up with those two answers is we would say x plus 1 equals 7 or the opposite of x plus 1 equals 7. So here x is going to equal 6. Here negative x minus 1 would equal 7. So negative x would equal 8, which would make x equal negative 8. Okay? So our goal is to get the absolute value by itself, and then we write it as two equations. The equation equal to the number, or the opposite of it equal to that number. Well, the problem is we have two absolute values. If I had two square roots, I would want to separate them, because then if I square both sides, would I get rid of both square roots? But with absolute value, you can't get rid of it, so you've got to put them together. So I'm going to move this one over. And so it'll become plus, and then we're just going to write it as if though there are no absolute values in the equation. So 2x minus 5 plus x minus 3 equals 4. And then I'm going to do the opposite of 2x minus 5 plus x minus 3 equals 4. So here, 2x and x's. 3x, and then we have a negative 5 and a negative 3, which is a negative 8. If I move over the 8, I would get, and so x would equal 4. Here, if I distribute that negative, negative 2x plus 5 minus x plus 3 would equal 4. A negative 3x plus an 8 would equal 4. A negative 3x, if I move the 8 over, what am I going to get? So x would equal 4/3. Now, here's what I'm going to tell you. We looked at all of these things in pieces last year. So, you have a general concept, or you should have a general concept of each of them and how to do them. So now you're just going to have to take them and apply them to bigger problems. And I might mix a square root with a rational function. So deal with the square root, deal with the rational, just deal with each one individually and then put the pieces together. Okay? So today is going to be a little bit more intimidating because you're going to start putting those pieces together. But don't let it. Look at each one separately and then put them together. Don't try to evaluate them together. Evaluate them separately. So remember our parent functions for yesterday. Line, domain is all real numbers. Parabola, domain is all real numbers. Absolute value, domain is all real numbers. But when we get to square root, do we have a restriction? Okay? So anytime I have a square root in a problem, do I need to worry about the restriction on that square root as a part of that answer, a part of whatever I'm doing? Okay? Exponential has no restriction on its domain, but does exponential automatically have a horizontal asymptote? Yes? Okay? Log, because it's the inverse of exponential, it's going to have a restriction on its domain. It's got to be bigger than 0, and it's going to automatically have a vertical asymptote. So those are things that you have to know going into those concepts. All right? And then the last one was your rational function. So here was your parent rational function. What makes the vertical asymptote? zeros on the bottom, okay? What makes the horizontal, we'll review that in a moment. But remember, it has to do with the degrees of it, but I'll write it down for you in a moment, okay? And then the only other thing we graphed last year was the polynomial function, where we just, remember, plotting the dots and just kind of weaving in and out. All right. So I'm going to have a bad habit of saying, remember last year when I told you, because like half of y'all were in my class last year. Remember the worksheet I gave you? Okay, it doesn't matter whether you have me, Miss Winstrup, or Miss Lininger, you got the same worksheet. And they said basically the same thing. So it might not have came out of my mouth, but it's just going to come out of my mouth because so many of y'all were in my class last year. Okay, so when I say remember last year when I told you, I physically may not have told you that, but I promise you were told because we all use the same notes, we all use the same everything. So just pretend I was whoever your teacher was last year. We good? All right. So yesterday, and I am also currently videoing what I'm saying, so I filled this all in, and I will scan this in, and all of this with the notes in entirety will be put on Schoology, okay? Today we have a really big packet. It's got a whole lot of words in it. When I tell you you really need to write this down, then really write it down. The rest of it, I wouldn't worry a lot about it. It's very intuitive. It's very common sense. So you'll be able to do the homework tonight without all of these notes because it looks exactly like it sounds, okay? So I'm going to flip through them quickly, but remember, they'll be there for you to go back and look at more slowly at your leisure, okay? So the things we're going to talk about today: function, definition, and notation, domain and range, continuity, increasing and decreasing, boundedness, local and absolute extrema, symmetry, asymptotes, in behavior. You talked about all of that last year except for boundedness. Okay? So domain. A function from a set D to a set R is a rule that assigns to every element in D a unique element in R. The set D of all input values is the domain of the function, and the set R of all outputs is the range of the function. Is there anything new and secret in that paragraph that you have not known before? And that didn't come from Algebra 2. That came from a long time ago. Okay? Function notation. I'm sure you've all seen f of x before, correct? That's function notation. X is the independent, y is the dependent. Mapping. Ever seen those before? Okay. Is it okay that it goes to the same place? Is it okay that it comes from the same place? No. So function, not a function. Have I just, everybody's good, right? Vertical line test. You ever heard of that before? So here's some graphs. Function? Yes. Function? Yes. Function? No, because it does not pass the vertical line test. Agreement about domain. Unless we are dealing with a model that necessitates a restricted domain, we will assume that the domain of a function is defined by the algebraic expression is the same as the domain of the algebraic expression, the implied domain. So the implied domain of a parabola is all real numbers. Agreed? Okay. Now, do y'all remember our vertical motion problems where we had a lot of upside-down parabolas? And did we forget about all of this part of the parabola and all of this part of the parabola, and we were only dealing with from here to here? Okay? So, for models, we will use a domain that fits the situation that is the relevant domain. So, this is the implied domain is all real numbers. But for this situation, it's only going to make sense from here to here, so that is the relevant domain. Okay? If I don't need to make it relevant, then I'll just use the implied domain of all real numbers. So, to find a domain of a square root, we know that that one has a restriction, right? What does the square root do? It moves it left 2. So everything bigger than negative 2. If I don't want to think about it that way, then all you have to do with the square root is take what's under the radical and make it greater than or equal to 0. And so x would be greater than or equal to -2. And PreCal is only going to write it like this. And I hate that we had to spend so much time last year with Set Builder, but the book is filled with Set Builder, so if you're going to use the notes out of the book, if we don't go back and forth, the notes didn't make sense, okay? So you need to get accustomed to writing everything in interval notation, okay? I will not read that -2 to infinity. I will say x is greater than or equal to -2, but that's how you've got to get in the habit of writing it. Okay. Now, here's where it gets tricky. Do I have a rational function? Yes, because of that x in the bottom. Do I also have a square root function? Okay, so I got two things I got to deal with. According to this, does x have to be greater than or equal to 0? According to that, x cannot equal 5. So, my domain is everything bigger than 0, but it cannot equal 5. So how do I write that? 0 to 5 union 5 to infinity. All right, why did I put a bracket? Because it can be 0. Why did I put a parenthesis? Because it can't be 5. So, does this mean starting at 0 and keep going, 0 to infinity? If I start at 0 and go to infinity, does that mean start at 0 and keep going, greater than or equal to 0? And I put that so that I would remove the 5. Okay? Now, if I take that square root off, is this all I have to worry about? X not equal to 5. Yes, because now my top is a what? What is just plain x? A line, right? What restriction do we have on a line? We don't. So what are the two that we have to think about restrictions on? Square root and log, and then anything that makes a 0 in the bottom. All right, here, if I remove all of this, that is a what? Something, something, s squared is a parabola, quadratic, with a domain of all real numbers. But when I cover that, then I just go from an implied domain to a relevant domain, okay? Because I'm saying S has to be the side of a triangle. So even though the implied domain is all real numbers, relevant to this situation, S has to be what? Greater than or equal to 0. So that my area and side don't become negative. And it's arguable about whether you even include the 0. I don't think it's going to be a point of contingency, because technically S couldn't be 0 either, because then the triangle wouldn't exist. But typically most sources will go ahead and include the 0. All right, now, finding range is another can of worms. Domain, we know the restrictions that it can't be. Range is what the graph ends up doing, okay? So for this one, this is that parent, 1 over x, just stretched by 2, which is not really going to change much of anything. So is that what that graph is going to ultimately end up looking like? Oh, is that what that graph is going to ultimately end up looking like? And maybe sometime today it's going to focus. All right, well, it's not focused, but you can kind of get there. There it goes. All right, so what is my range? Everything except what? 0. So y cannot equal 0, so my range would be negative infinity to 0, 0 to positive infinity. And the u is just union, to join them together. Okay? Now, this is where I told you I would go back and review the asymptotes with you. Why did I know that asymptote was 0? Well, you knew it from the graph, but you should also know it from the equation. Okay? So, the number 2 has a degree of 0. X has a degree of 1. X squared has a degree of 2. X cubed has a degree of 3. So when we looked at rational functions, if the degree is smaller on top, it's automatically y equals 0. When the degree was smaller on the bottom, there is not a horizontal asymptote. And when the degree was the same, let's see who can remember. If I had 2x cubed over 3x cubed, what was my asymptote? What does that mean? It's not 1. Y equals 2/3. Remember, you use the, is that what you were trying to say and you just couldn't figure out how to say it? Y equals 2/3. You use the coefficient. Okay? So, that is something, if that did not come back naturally to you just right then, you might need to write that down, because you are going to have to understand where the asymptotes are. Even if you graph it in a calculator, you have to know where that asymptote is, because sometimes the calculator just quits drawing the graph because of the pixels of the calculator. So you have to understand where the asymptotes are. In most cases, range is going to be easier to make yourself a picture and look at it, or if it's something really messy, graph it in the calculator and look at it. Okay? I expect that you can visualize this picture on your own without a calculator. Okay? All right. Continuity. This is continuous. Can I draw the thing from left to right without picking up my pencil? This is discontinuous because it has a what? A hole. Okay? This is discontinuous because it has a hole. This is discontinuous because do I have to pick up my pencil to get from that piece to that piece? This is discontinuous because, again, do I have to pick up my pencil to get from that piece to that piece? So continuous, all of these are discontinuous. All right? Forget about this for a moment. We'll address that when we need to. This is called removable discontinuity because it's simply a hole. We just removed that one little piece. We got that when the factor on top was the same as the factor on the bottom. Does this make sense to you that we might call this jump discontinuity? And that we call this infinite discontinuity. Remember what I said the words would make intuitive sense tonight. Okay? So there's a jump in the graph. This is infinite because we have a what? Asymptote. Not a hole. We have an asymptote. Okay? So this graph would be continuous. This graph would have removable discontinuity at 2. X equals 2. This graph would have infinite discontinuity when x equals 2. Everybody okay with that? Increasing and decreasing is exactly what it sounds like. From left to right, this is increasing. From left to right, this is decreasing. From left to right, this is constant. And it can have all of them in the same graph. Decreasing, constant, and increasing. And then you just have to say, it's decreasing on this interval, it's constant on that interval, and it's increasing on that interval. That makes sense? We good? Alright, so a function is increasing on an interval if for any 2 points in the interval a positive change in x results in a positive change in y. A function is decreasing on an interval if for any 2 points in the interval a positive change in x results in a negative change in y. Notice I said positive change in x both times. Negative, decreasing does not mean they're both going down. Remember, we are reading the graph from left to right. So x is always increasing, and if y also increases, then it's increasing, and if y goes down, it is, and if it doesn't change, it is constant. Alright? So, what would we call this one? Y is staying the same. Constant. Y is going down, so decreasing. Y is going up, so increasing.